Chemo and GelSight. So if you want to go ahead and introduce yourself, Chemo. Yep. And are you going to start with a presentation or are you going to start with a demo?
I should start with the demo because if I start with the demo, we'll never get to the slides. So I'll do a few slides first, and certainly feel free to interrupt at any point. I'm sure I have way too many slides, but happy to tell you the story of GelSight and how we got to our latest instrument, GelSight Modulus. What's really fascinating to me is if you look around at the types of technologies that are being built, particularly within the defense industry, but also commercial aviation, so much technology in the design, manufacture, and even in the operation of these platforms. But the lifetime of these platforms is measured in decades. And if you look at the types of technology being used to inspect them, it's certainly nowhere near at the same level. And it's actually generous to call it 20th century inspection technology, because a lot of times people are scratching surfaces with their fingers, looking with their eyes, and trying to make assessments. Is this still fit to fly? Using hand tools or traditional NDT, that's really the space in which maintenance decisions are made today. And if you look at reports on how much of our fleet within DoD is mission capable, it's embarrassingly low. 42 out of 45 missed the mission capable goals, a lot due to corrosion. That's motivating. How can we bring newer, more modern digital tools into the maintenance workflows? So I'll tell you, I have a lot of slides, as I said, far too many, but I'll try to get through how GelSight works, the technology, and really this device we've developed with Army funding, GelSight Modulus, our newest tool, which has been great for us. We've passed 100 units sold in less than a year, which for this platform is really great. We're seeing a lot of excitement around it. So the GelSight technology really started when I joined Professor Ted Adelson's lab at MIT as a postdoc. He had this idea of turning touch into an image. He had made this block of gel that you see in the slide, and he had the original idea, which is what would happen is if you had a flexible coating on the gel, and you could press something into it and look through the other side, such that you're seeing the coating itself, you're not seeing the object. He asked me if I could measure 3D using this technology, and I developed the first 3D imaging systems, both the hardware and the software algorithms, and we published papers on this in computer vision and graphics conferences back in 2009 and 2011. We also made YouTube videos to go along with this technology. And one of the videos after our second paper shot up to almost 150,000 views within a few weeks, which for an academic video wasn't too bad. It's also surprising how many people are watching YouTube at work, because after I presented that technology at a conference, I had over 1,000 emails in my inbox from people in many different industries asking how they could get access to the technology and how they could use it for their different applications. And lately, YouTube has continued to be a great source of leads for us. A technology content creator out of the UK, Steve Mould, has taken a liking to our technology, and every once in a while makes videos. I would almost admit describing it better than many people on the team here, because that's his business, is to describe technology to a broad audience. That leads to millions of views and easily thousands of emails again within the course of just a few days. So as of today, we're a small business based out of Waltham, Massachusetts. Our core technology is licensed from MIT. We also have a broad patent portfolio around that core IP. And we're also active in government contracts, done several SBIRs, TACFI award right now with the U.S. Air Force, and certainly always looking for opportunities to collaborate and continue to develop our product roadmap. So when we first demonstrated this technology at computer vision and graphics conferences, the reaction was, wow, this is really cool, but what is it good for? And honestly, at the time, we said, we don't know. And it was really that inbox full of emails And after we had our first product, it was the market that told us various applications. Consumer goods, measuring different features on them that we didn't even know industrial designers cared about. Certainly within space is one of our fastest growing applications now. Inspecting components so that they can be relaunched, making sure that they're still within specifications. Commercial aviation is our single biggest market today.
So let me stop you there for just a second, Kimo. So what you showed us was an inch, that sensor. Do you have larger sensors for larger applications?
We could make the technology in a variety of different sizes, but as of right now, it's really the small dimensions that people care about. So the way to think about it is that our technology fits into existing inspection workflows where you have somebody who's looking at a component. Like let's take the fuselage of the 737. We're not going to scan the entire 737 at micro-inch resolution. They have teams of inspectors who are looking over for any scratch or dent. Once they see the scratch or dent, the question is how deep is it? And is it in spec or do we have to repair it? So the detection task is already covered by current workflows. It's the measurement task and the characterization that needs digital tools.
Okay, thank you.
Yeah, and that's common really with all these applications. Even with consumer goods like sunglasses, there's certainly on plastic glasses, there's the parting line. When you're doing injection molded plastics, you have the mold that comes together. And as that plastic, if it seeps into the seam between the mold, you can get a little raised ridge. So they know where to inspect in this location, in that specific component, but they have a tolerance on how high they allow that ridge to be, because of course, if it's in the nose piece, it's going to be uncomfortable for people buying those sunglasses. So in some cases, they're relying on visual inspection to see if there's a defect. In other applications, they know where to inspect, and they have specifications around tolerances on certain locations. Low observable coatings, same process of looking over the skin of the aircraft and seeing if there's any damage and trying to see if the damage is increasing in size over time. Because if you have damage to low observable coating, it can affect its stealth capabilities. Even toys, like really, and everything on the slide is a real example of how GelSight can be used for quality control. It also has interesting science applications. At the time we started the company, I didn't know there were over 1 million fish in the basement of Harvard. And a guy got his PhD measuring fish skin surfaces, which does have applications in shipping, looking at the different, like friction capabilities of marine coatings. This is me in the basement measuring this shark, which unfortunately was fortunately for my purposes dead, but it had been in this tank probably for years. So you release a platform technology, you never know the potential applications. Measuring sharks is not the money-making application, but certainly aerospace and space have been really where we've deployed a lot of systems. Now the technology, the real concept is to turn touch into an image. Here I'm showing one of our sensors. When you press an object up against the surface of it, it reveals a lot of detail about whatever touches it. You can see down to the pores of my fingerprint in this image. And conceptually, the pad of this gel is like your skin. It's going to deform when it touches things. And the system is like what would happen if you had cameras inside your skin. You could see how your skin deforms. So the camera captures a digital image of that deformation, which is a way of digitizing touch. And I'll show you why that's interesting for measurement. So many surfaces are optically complex. Here is a common abrasive. If you look at this surface under a microscope, this is what you see because the light is bouncing inside these transparent crystals, reflecting within them and refracting, and then even reflecting off the surface. You'll get these specular highlights if it hits like the mirror reflection angle. So from just an image of a surface like this, the material properties make the image difficult to interpret. When you press the gel up against the surface, you're optically filtering those properties and making the image easier to interpret, but also easier for algorithms to measure. Because we replace the material reflection properties of the actual object with engineered reflectance that we can create on the surface of the gel. And this is really important for a lot of common materials that are in industry. Metals, which are shiny, composites, matte black surfaces. I'll have another example of that later in the slide deck. But when you take the GelSight image, it makes a uniform reflectance, and then we can use our controlled imaging and algorithms to turn that image into a 3D measurement. And in this case, we can even see this microprinting on this Japanese coin. How have we turned this into a product? We have our handheld probes, which are really just a camera. You have a camera, a lens, light sources, and the gel. And it's the images from 6 different light directions in the probe that give us the information we need to calculate a detailed 3D map of the surface. And the standard workflow, and I would say that this was actually something I learned in commercializing the technology. People really didn't care about a 5 million data point map of the surface. What they want to know is a single dimension typically. What is the depth of this defect? Length, width, and depth maybe? Or what is the roughness of this component? There's a dimension that can help them make a decision. Can they accept the component? Do they need to repair it? Do they need to replace it or scrap it? So we can get from, let's say you see a scratch on this airplane wing, snap a scan of it with the device, and within a few seconds, have a digital report that tells you the dimensions that you care about, can go to a material review board who can tell the artisan, yes, you can blend that out, or no, this part is scrap because it has a crack in it.
So the bottom of that, I'm sorry, the bottom of that image, that's a cross section at that point, at that line?
Yeah, it's a single cross section through the deepest point that it's sectioned.
Okay.
Yeah. And in this case, the defect is automatically found within the field of view, but certainly not automatically found on the aircraft wing. You're relying on a human inspector to see it with their eye and then press the probe in the right location to get the measurement. So we have various different probes. GelSight Mobile is our workhorse. It's been on the market for a few years now. I think we released that around 2020. Actually started developing it in 2020, released probably in 21 or 22. GelSight Max, highest resolution device that we make, higher pixel count camera and a higher magnification lens in it. It is a larger device, mostly useful for R&D. This one is used a lot by a forensics customer who's scanning cartridge cases, looking at the fingerprint that happens when you fire a bullet out of a gun. That cartridge case gets the firing pin impression on the back side, which can allow you to trace that back to the weapon that fired it. So they're using a lot of GelSight Maxes for forensic investigations. And then GelSight Modulus, our newest product, which was funded with R&D funding from the Army, and I'll tell you about the story of how that came to be. With our GelSight probes, we have a much larger list of customers than this, but this is the list of those that we can talk about publicly. We estimate more than 80% of aerospace companies are using this today, some of them with many tens of systems deployed in production. And space, as I said, is the fastest growing application, with these space vendors functioning much more like startups than traditional aerospace companies, where there's a lot of bureaucracy and overhead in getting systems like this deployed. Customers who use our systems love using them because of the ease of use. If you have any experience with metrology systems like confocal microscopes, interferometers, you almost need a PhD to operate those systems. Being able to tune the exposure parameters the way you need them, set the start and stopping point of your range of scans, whether it's an X, Y, or Z, waiting 20 minutes or 40 minutes to get the scan and then seeing if you got a good result or having to start over if not. But GelSight, it's really point and click. You just press it up against the surface, press a button, and you get a measurement. So with Modulus, this really came about when we had good traction into aerospace, commercial aerospace, and started thinking about who has the largest fleet of aircraft in the world. Of course, it's Department of Defense. We got connected to an Army aviation group who was willing to work with us on adapting our system to their applications. At the time, we only had our Series 2 device. We had just released that. But when we saw the types of components that they wanted to measure, it was really obvious that our current probes couldn't fit in these nooks and crannies that they wanted to inspect. We did on-site visits to Fort Eustis, Corpus Christi, AFSOC, SAFA, Sun, Fort Campbell, and saw the kinds of components they needed to inspect. And that really drove the list of requirements of how we wanted to move this product. And also we listened to their current inspection methods. And a lot of inspection starts with visual inspection, whether it's on the aircraft itself or on components after it's been disassembled. People are looking for any sign of an imperfection. And if they see anything, there's a lot of value if you can give them a tool that can capture a digital image of the issue that they see. Because what happens today is as soon as if they're looking at a component, if they see a little issue, they'll send it down to NDT, like dye penetrant or these other techniques, so they can try to get data about it. Because with just your eyes, you might suspect something, but you can't confirm. Is that a corrosion pit or is that a crack? But visual inspection is really the first level of inspection in many maintenance workflows. Okay. And then for NDT, dye penetrant, eddy current ultrasound, these are very commonly used methods, requires training. We learned a little bit about the training protocols required, whether it's level 1, level 2, level 3, who gets to write inspection maintenance, our NDT protocols versus who gets to execute them, and then how some of these techniques need to be tuned to the specific part being inspected. Like if you're inspecting aluminum, you need to get out your tuning block or your test block for aluminum and like tune the gain knob on the probe to make sure you're getting the response you need on that. Or dye penetrant involving hazardous chemicals. And even for these techniques that require like dye penetrant, you're looking for like a fluorescent response. One of the inspectors described to me how they have to do this on helicopter blades on a sunny day by putting a blanket over their head with holding a light and trying to see if they can see this kind of fluorescent crack in the blade, which is certainly not an easy workflow. And then another story around the inability of eddy current to distinguish between corrosion pits versus cracks. This component I'm holding here, they had issues with this at CCAD, where if they got a ping on the eddy current device out in the field, they would take this top cover off the helicopter, ship it all the way back to Corpus Christi. And if they find out that that ping was caused by a corrosion pit, it could have been repaired in the field, maybe even in situ. But cracks are considered enough information to scrap the component and replace it with a new one. Cracks are not acceptable. Corrosion pits can be buffed out. And the fact that this is removed from the aircraft is unavailable for missions while it's waiting for this component to come back from halfway across the world. So the ability to have an in situ in the field digital record of is it a crack or is it a corrosion pit has a lot of value in streamlining those maintenance processes. So once we saw the variety of components that were being inspected on our daily basis, it was pretty obvious that there's no one-size-fits-all solution to this, which led us, and also the fact that visual inspection is driving a lot of these decisions. This is another story of seeing this helicopter blade that had passed visual inspection. It was a matte black helicopter blade. When the inspector told me where they typically find cracks, I put the GelSight probe on it and got the scan you see here, which showed that there was a crack that had escaped visual inspection. And they did confirm it was there after I found it and said, okay, well, they were fortunate we had been on site because this would have gone on the helicopter and potentially failed in flight. But it shows the challenges of visual inspection. Maybe 8 a.m. on a Monday, you'll have an easier time seeing these types of defects. 5 p.m. on a Friday, probably miss a lot of things that, especially on a matte black helicopter blade that's if you're like, over the age of 50 and need, progressive lenses, it's going to get harder as you get older. So with GelSight, you have the ability to have a digital record and it's image data, so it could be trained to automatically detect these as you're scanning it across the blade. So again, certainly was obvious that there's no one size fits all. And it's honestly, the applications that we saw are really demanding smaller inspection tips. Our current product ships with 16 millimeter straight and 90 degree. We just released a 20 millimeter, slightly larger. But there's the next one that we're working on, which was funded by this Army program, so I can talk about it, is like a pencil tip to go into these tight corners and see if it's a corrosion pin or a crack to help make that decision and get a digital image to know if this component needs to be removed from the aircraft or if it can be repaired in place. So in this program, we had to prove a number of different technologies to make this happen. Can we miniaturize the optics? That was what we did in the first prototype. The second prototype we built into the program was about modular tips, being able to swap the lenses and still do GelSight measurements. And then on our final iteration, developing the angled tip that we could get inside different components, inside bores or tubes, which was something that a GelSight system before that could never measure. And software feedback, we received a lot of feedback along the way around how can you measure larger areas. And with this, in our single probe, we developed stitching algorithms where you can take multiple scans and blend them together and do a single measurement. And also, not just 3D measurements, like depth, being able to measure two-dimensional distances, like the distance between an edge and the center of a hole, diameters. There's a lot of rich two-dimensional information in all of our scans. So we developed software features based on requests from people using the devices in the field. And then as part of our development of any device, we go through MSA studies, that's measurement systems analysis, where we start with a set of certified plates and do repeated scans with multiple users, multiple devices, multiple gels to make sure that we understand the system variability that can help us define the specifications that go on the spec sheet for the device. So let me go through a few applications of how people use this today, and there's many more than I can share here.
I'm going to stop you there and see if there's any questions at this point.
Sure, I'm fine. Yeah.
Quick question, Jacob Miskey here. I've been doing some work with a Keyence profilometer that uses structured light scanning, and I've noticed some drift over time. And you just mentioned the calibration standards you use. Do your probes have to be sent in for recalibration at regular frequency? How does that process work?
I think with respect to drift, it's actually an advantage that the gel is a consumable. And every time you swap the gel, you calibrate the device and it gets locked into known reference standards that we ship with the system. So once the gel is calibrated, we also have a second plate called a validation plate. And you can check that it's still measuring correctly by doing a couple of quick scans on the validation plate. We have an automated routine that tells you you're still within spec, or if it fails the validation, you can try recalibrating the system. or you can just replace the gel and start over. So they don't get sent in, but we do have some customers as part of like an annual maintenance program that they will choose to send it in, but it's not standard practice for the instrument.
Understood. Thank you.
Yep.
And now you talked about using these in situ.
Yeah.
I'm guessing that they're designed for that environment. I mean, is it something that can be carried on an aircraft or carried in a backpack?
Yeah, it's a pretty simple device. The probe is small enough, and it has a lanyard typically, so you have it around your wrist in case you drop it. It's not going to, hopefully not fall on the ground. And then it's powered by a tablet or a laptop, so it doesn't actually store any data on the probe itself. The probe is just a camera, but it's normally shipped with a Microsoft Surface tablet, and you do have the USB cable, but it's reasonably portable. So you can, walk around the factory floor with it and make a measurement. It doesn't have a cart or anything like that, like some other instruments do.
All right. Thank you.
And on this slide, you're actually seeing the full kit. A Series 2 instrument being held here, and then the tablet that's powering it and doing the compute with the interface to do the measurements. And then running our defect detection routine, it tells us this scratch is about 0.17 inches long, 23 thousandths wide, and 8/10,000ths deep at the deepest point. And you can send this report to your material review board, and they say, okay, it's less than a 10,000th of an inch, or less than a 1,000th of an inch. You can blend that out, and the part is good to be mounted onto the engine. This is a fairly common workflow for our tools. And before our tool was being deployed at many of these facilities, what they would have to do, once they see this kind of scratch, they would likely call in a team or an individual to come make a replica. So you mix together a 2-part material, like your A and your B, mixing them in your fingers until it's a uniform color. You press it up against the surface, wait 10 minutes. You fill out some paperwork about the serial number of the component, the platform, probably all sorts of information like time and date. Stick it in a bag with the paperwork, send it off to a metrology lab where it's on a queue of measurements that someone needs to process. They'll get to it at some point. If you're lucky, you get the measurement back in 24 hours. But we've heard from some of our customers, those processes could take a week, or maybe they even have to send it offsite because their internal metrology lab is too booked up to process it in any timely manner. So the fact that you could get this digital report on the factory floor within seconds and get that digital report over to someone to review right away can really streamline both new production inspection and also MRO processes. And that's really the workflow that we're modernizing. And you have a digital record as well. It's not like this, this one physical replica. You can archive this GelSight measurement in a database with your digital twin of this component if you're that sophisticated. Some of our customers are getting to that point. But having digital measurements can unlock a lot of capabilities in the future. Corrosion. When we're measuring corrosion, we can tell you that your pits are at least as deep as what we're measuring here. This is saying this is in millimeters, 0.24 millimeters. We found that's our deepest pit. And you can make a decision to try to grind these out and remeasure them. But the device is best for early corrosion detection, trying to measure the number of pits, the coverage of the pits, the density of them. But corrosion is certainly a big problem in military assets. And it's something that we want to understand more, how we can make solutions that can help combat corrosion. Fastener flushness. I think there's over 300,000 fasteners on a Boeing 737, and they all need to be flushed to within a tolerance. And today, people are running their hands across it to try to feel if there's any that feel out of spec. But we can give you a digital measurement of how flush it is. And that can tell you if the aircraft is meeting the specifications that were intended. Also measuring the holes before you insert the fastener, you can tell if the chamfer has been drilled correctly, has the right dimensions. So really, there's a broad range of applications. And because our system uses image processing and computer vision, we could design automatic analysis of these features from the GelSight images and 3D data to give the customers what they want. In many cases, it's a pass-fail decision or just dimensions. Yeah, go ahead.
If you go back to that slide, this is Eugene.
Yeah.
So what is the time for this process that we're looking at here? So I'm going to check a rivet, and it's just touch it, and that's it. I mean, you don't have to move it around. Do you have to? I mean, is it 1 second, 5 seconds, half a minute?
It's more like half minute when you get through, because it does take time to do the 3D processing and then the analysis of that 3D result. And when I do the live demo, you'll see it. It does take a few seconds, but certainly probably takes longer for somebody, or as long for somebody to go from one fastener to the next. And we can have our system even batch processing them. It makes a queue of measurements that are being worked on as you do the next one. So the fact, if it's processing one, doesn't stop you from taking another one, but it's not instantaneous. So it does take a few seconds.
Okay.
Yeah.
Thank you. And then just to let you know, you got about 18 minutes on this. I don't know how long you want to.
Yeah, and certainly we have plenty of time to take questions and play with the device as well. So,
okay.
So surface finish is another big application for us. A lot of times people think about finish in terms of RA, which is a linear measurement made by a profilometer. But for more complex surfaces, like shot peen surfaces, or more advanced surface textures, a single linear RA is not a sufficient measurement to describe the texture of the surface. There are other measurements like SA, which is the area version of RA, but the instruments available to measure SA are typically lab instruments like confocal microscopes, and you can't bring that down to the factory floor. You're certainly not going to be able to easily do a confocal microscope of measurement of, let's say, like low observable coating or shot peened surfaces on a landing gear. So the ability to have a handheld tool that can give you SA can really streamline some of these assessments of, is this part that's being machined to the right specification? Because aerospace specs might tell you need to meet like an 8 micro-inch surface finish on these components in variety of locations on the components. And that poses challenges for measurement, because fixturing a profilometer to get the measurement is also an art. Can take a long time because it's like a record needle, which certainly people younger than me might not even know about, but you're going to drag it across the surface and you need to have it normal through the surface. And it doesn't work well on curved parts. It's going to be hard to get it to follow that curved part. So GelSight provides a much easier way to get surface finish measurements. And where are we going next? This Army-funded development around Modulus actually got us connected to other groups within DoD that are interested in research on new technologies. And we've been working with a great group out of Warner Robins Air Force Base on extensions to our platform. One of the problems we're looking at is how can we track the probe around the factory floor and also track the measurements with respect to the aircraft, so that you can know that this scratch was measured at these coordinates on the aircraft. let's say you measured it on Monday, the aircraft goes out, comes back, you measure it on Tuesday, you can see if it changed or not, if the crack's opening up or if the damage is growing in some way. The ability to track spatial locations of the measurements can give you a lot of insight into how the platform is wearing. And actually, there was a funny story from one of these Air Force bases, which was they kept discovering corrosion increasing on this one particular component. And after they thought about it in more detail, they realized that it was because people weren't closing the latrine door, and you're getting urine all over this component, increasing the wear patterns and the corrosion of it at a much faster rate than the rest of the aircraft. So being able to see hot spots for wear patterns happening on your aircraft or across the fleet can provide you with insight and predictive maintenance, like analytics that can inform maintenance decisions going forward. So when we typically take a GelSight instrument to a customer location, we don't even show slides. We just say, let's go to the shop floor and let people show us the kinds of parts that they work on. So I'll do that demo here.
Okay, so while you're making that transition, there's a question I have. So
yeah,
there's an application that for acoustics where they're taking two hemispheres, they're making hemispheres and then they're matching hemispheres based on different properties. The hemispheres are each cut into 4 sections. So you're dividing your hemisphere in half and then in half again.
Yeah.
Now this is probably 3/4 of an inch high. I don't know that you have a gel that would be that thick that you could wrap around it, but would you be able to use the pen to go over the whole surface and it would say, okay, this is what each quadrant of that hemisphere looks like and tell you whether they're off by whatever distance?
Yeah, it's with that application. I guess my first instinct would be that our system is not well matched to the application. The system is really best for surface finish and surface quality issues.
Okay.
For example, I'm showing my fingerprint here live. And for something like the gross dimensions of, let's say, hemispherical quadrant, it's certainly not a great match for that.
Okay.
For a number of reasons. I would think that something that's capturing the more large scale geometry would be a better system for that kind of measurement.
Okay, yeah, and that's what they're using. They're using a laser light measurement system. I was just curious.
Yeah. So let me show you here, for example, just showing you how the system works, pressing it up against this abrasive. And then in a number of seconds after I press the button, it's already computed the 3D, and now we have the surface roughness analysis showing you this has a certain RA. We can also look at the 3D map of the surface just to see what it looks like. But for the most part, people just want to get this number out of the system, and we can go very quickly to a PDF report. I can tell you if that's the dimension you're controlling, has a table of different surface roughness outputs, different parameters. And that's the general workflow. It's just a quick measurement and then a quick report. Let me get to something like this one. Let's say that you see this damage on your aircraft wing. You see, it does take a few seconds to calculate the 3D data because it takes 6 pictures very quickly. I'll show you the 6 pictures. When I press the button, it takes pictures with different light directions. And then the algorithms that I've designed take that to a 3D model that I showed you before with this, but here's a 3D model of the dent. And then for this application, we're not so interested in surface roughness. We could look at defect detection. It's going to tell us length, width, and depth of this damage. The depth is about 13 thousandths of an inch. And so then if you're a maintainer, you can say, there's this hail damage on our wing, 13 thousandths of an inch deep. What do I do? They can say, okay, you've got to buff that out to an inch, blend it out. Or, I'm not a maintainer, so I don't know exactly how they handle these things, but the fact that you have a digital record showing the measurement all within less than a minute, that has a tremendous amount of value to our customers. And other measurements, that would be very challenging for many systems. Let's say you're inspecting an engine and you see on one of the blades a ding in it. And because we're measuring the deformation of the gel, we have no problems with leading edge of a blade. Leading edges can be challenging to measure because you have a metallic part that's curved. And so at some point along that curve, you're going to hit the mirror reflection angle, and you'll get dropouts and specular highlights that make the measurement challenging. So for our system, we just let's get rid of this. Take a profile across that edge. In this case, I'll level the profile on each side. Then we can say that it's 20 thousandths of an inch deep. And that depth can also inform, do we need to pull this blade? Or what, how do we repair that? Do we just grind it down? And having that digital data helps you make a quick decision. So this again is GelSight Modulus. And we've got a replaceable lens. And the gel itself is also replaceable. So we sell this with a kit of lenses, straight and 90 degree. And then when the gel wears out, you can replace the gel on the tip of it. It's a consumable in the system.
How do you know when a gel wears out? I mean, are there indicators?
There's a general guideline in the software that's looking at how many times it's used. So it's counting the uses, and I think when it gets over 300, it starts to kind of glow red. But typically our users are trained as part of the initial setup of the device. We teach them to look for signs like missing pigment in the gel. Like if you start to see holes in it, or if you cut it, it becomes obvious in the image that it's damaged. But it is still part of training that someone needs to learn to detect the signs of wear. Just see, does the gel still look good? Or if it's picking up like metal shavings that are embedded in it, then again, it's part of training to know that you shouldn't be using it if it's picked up a lot of debris that you can't get out of it.
Okay.
Okay, I see a question, Brian.
Yeah, I'm curious. I have 2 questions. One is, could you use one brand new calibrated gel tip to measure the wear and tear of an older tip? And then my second question is, if you had a wish or your dream or goals or whatever, what are some projects that you would really like to see this used in?
Actually, I think the inspecting large surfaces is a great application. If we go back to that story I told about detecting the crack in the helicopter blade, that's something where it did require expert knowledge. When the inspector told me where there's normally a crack, I put the probe down and I found one within a few presses. But I can imagine a solution where you've got a large area scanning GelSight, maybe like a paint roller, imagine that, and you can just run it down the surface and have it automatically find cracks and issues like that. So that would be because we've gone smaller and we can do small scale measurements, very localized measurements, but the ability to go bigger would broaden the use cases.
Yeah, I'd like to see something like a 12-inch diameter tip.
Right. Yeah.
Large areas.
So chemo, if you can get into it, how would you end up using multiple cameras for that application? Don't give up your IP or anything here, but
we do have IP on that, and so
okay.
I think another way of doing it, accomplishing the same goal, which I can talk about because it was funded work by the Arm Institute with Boeing and some collaborators at CMU, is you can solve the detection problem using other systems. In that case, we used just imaging with structured lighting to find potential defects on the surface. And then once you've found the potential defects, you have a robotic arm that goes in and measures them with GelSight, because the problems of detecting and measuring are two different problems. And the detection problem, using machine vision and AI, you can already do a good job finding potential areas of issues, areas of concern. And then with GelSight, you can get the quantitative data showing how deep it is. So you don't have to do everything with the gel, because making the gel large enough to cover a fuselage panel of a 737 is really not feasible. But then, roller is another approach. But the roller is also assuming that you've got a component that's either nominally flat or lightly curved. So there's certainly different strategies that we can think of, and it just depends on the application what we think might be the best way to solve it.
Okay. So then we've got just a few more minutes here. So what can we do for you? What can the community do for you? Are you looking for additional investment? Are you looking for, somebody within the aerospace industry or within the Department of Defense that would be interested in funding this? What are your asks?
We're certainly always interested in connecting to people who have different applications, whether it's in industry or within Defense Department. Because as I did mention, we're doing funded SBIRs now. And so we're open to new opportunities like that. Because if we can find good alignment between the needs in our product roadmap, then we can think of a project that kind of satisfies both, which is what we've done with the Air Force, putting spatial tracking on this device so that we can know where the measurements are made. And the other funded project we have with the Air Force is on robotic tactile sensing, putting GelSight in the fingertips of a robotic gripper so that it can feel what it's grabbing. So we do have a platform technology, and there's many applications. So finding people with interesting problems where this could be one solution, and I think we're always interested to collaborate.
Yeah, I never thought about that, the robotics application, because that would be a great pressure sensor. If it were to grab an empty aluminum can or something like that, then it would stop at whatever depth, which would be predetermined as to, what kind of friction area you have to versus the weight or the fragility.
Yes, and that was the original inspiration for GelSight technology, being a soft representation of the human fingertip. And there's a lot of work. The professor I worked with, Professor Adelson at MIT, his lab after I left converted completely into robotic tactile sensing and showed a lot of different applications, because you can tell not only how hard are you grabbing it, but you can tell if there's slip in the grasp, the orientation of a component in the grasp. And that type of information can tell you the forces that happen when you're trying to insert an object into another object. Like, think about inserting a plug into a port. You do that by feeling the port push back from the plug, and then you jiggle a little bit to get it to the line. So it's really a tactile manipulation. And the signals you're getting through your finger are similar to the signals that GelSight can get through how the gel is deforming in real time. So the robotics applications are very interesting, and we're working on some miniaturization efforts with our Air Force partner. But certainly finding applications where those types of robotic manipulators could really unlock new capability, that's certainly interesting to us.
And then looking at the difference between manufacturing and maintenance, is there, to me, it seems like it would have the same necessity in both, that there's, is there more necessity for like on the maintenance side for this, or more need for it on the maintenance side than there would be on the manufacturing side, or is it equal?
Yeah. The applications are really similar, and it was really part of our go-to-market strategy to first get this into new production inspection and get it to be qualified and used by the OEMs as part of certifying that their components are within their specifications. But then if you think about it, the fleet of deployed aircraft being maintained far exceed the aircraft that are produced every year. So it's a bigger opportunity to find maintenance applications. But it's really the same types of, I would suppose some of the measurement tasks are different, but it's the same workflow. Like in a maintenance application, you might be seeing wear on a component from components rubbing against each other. Corrosion is more of a maintenance issue. But scratches and dents are common both in new production inspection and maintenance. So the types of measurements might differ, but the use case and the workflow is very similar.
And then, so thinking of different industries, so I'm thinking, would there be applications for vibration where this would hover over or sit on the surface? Would there be applications for, something more fragile? Like, can you make a thinner GelSight tab? So like, if I was checking IC chips that are pre-bent, the leads are pre-bent or whatever, I don't want to bend them any further, but I do want to see, do a quality check that, when they come out of manufacturing, that they're going to work for a pick and place machine.
Yeah, GelSight is really great when you're dealing with multiple materials and you need to make assessments across multiple materials. I can imagine on a chip, you've got like an insulating material and then a metallic material. And if you need to judge alignment of one material with respect to another, it can be good for those measurements. But where it's going to have challenges is if you've got, let's say on the PCB, you've got raised components. If you need the gel to flow over those components, it can be a little more challenging, but we certainly have thought about some applications like that. And I think we've shown in our early papers on this that you can make the gel in almost any shape and size. We made it thin enough to measure the deformation caused by soap bubbles, and then thick and strong enough to measure the deformation of a car tire, like driving over it.
So there truly are unlimited applications for this.
Yeah, it's a broad space, and that's one of the challenges of commercializing it, is figuring out what is the single way that you can design and build it where you can sell a broad number of these for the same applications. And aerospace right now has been very good for us. But I know that there are many applications where this could really, transform different industries.
Yeah. Yeah, I'd like to bring you back for a 2-hour session where we just talk about applications.
That would be exciting. Yeah. I have certainly plenty of novel measurements which are not commercially interesting but fun to look at. And I'm glad that I didn't have to do them myself. I had to do the shark measurement, but one of my colleagues has measured snake scales and spiders, and certainly there are people looking at cell structures on leaves, biological applications. Norwegian ski team was using it to measure the snow texture before the race. It's wild. Once you give people a tool that can do, basic tasks like measuring a surface, there's so many surfaces in the world that could have functional properties that impact their performance. So there's broad applications.
Yeah. Yeah. So definitely we'll reschedule this for a longer presentation where we can delve into all of those applications.